All right, problem 1C, peroxide disulfate ion. So this is actually in the redox chart. This is like number 2, peroxide disulfate. Oxidizes iron 2 ion to iron 3. And is itself reduced to sulfate. This is it? Yeah. Okay. All right. We have to take a look at, whenever we have this type of net ionic equation, we have to make sure that the atoms are balanced and that the charge is balanced too. And so when I look at this, even though, well, maybe it's balanced. I have 2 sulfurs here. So I have 1 sulfur here. And so it looks like I need to put 2 sulfates there. And that will give me 8 oxygens over here. And so now all the atoms look balanced. 2 sulfurs, 8 oxygens, 8 oxygen, 1 iron, 1 iron. But in addition to atoms being balanced, we also have to make sure the charge is balanced. So the total charge on the left side should equal the total charge on the right side. And so this is -2 plus 2 gives us 0. And then this is +3 minus 4 gives us a -1 total charge on the right side. And so it's not balanced, actually. And so in order to balance this, how can we balance this? Well, one way we could try to balance it is by changing the irons. That is, what if we did this? What if we did 2 iron 2s going to 2 iron 3s? If we did that, then the total charge on the left is -2 plus 4 gives us +2. And then we have +6 minus 4. +6 minus 4 gives us +2. And so now the charges are balanced. And so we have to figure out some way to balance out the charges. In reality, that way that we normally figure out how to balance charges is we do it based on the redox chart. So this one's actually on our redox chart, and we can figure it out, or we could just figure it out based on skeleton redox. So we go S2O8 2 minus goes to SO4 2 minus. And we want to figure out what's happening with that. That's called a half reaction. And then we have one more half reaction. Fe2 plus goes to Fe3 plus. So if you write that over here, Fe2 plus goes to Fe3 plus. The quickest way of doing this is if we have a redox chart. And both of these occur on the redox chart. So we could copy these off the redox chart. S2O8 2 minus plus 2 electrons goes to 2 sulfates. The quickest way to get this one over here is just copied off the redox chart as well. Except we're going backwards here. Fe2 plus goes to Fe3 plus plus an electron. When we have the 2 half reactions, we have to look at the electrons here. Are the electrons balanced? So over here, this one produces 1 electron. Over here, this one consumes 2 electrons. Since the electrons are misbalanced or mismatched, what we have to do is we have to multiply this one by 2. If we multiply this one by 2, then we get 2 electrons produced, 2 electrons consumed, and then we combine them. When we combine them, then we end up with this equation over here. This is the equation we end up with. So both of these species occur on the redox chart here. What if they didn't? If the species doesn't occur on the redox chart, we have a technique for balancing these. So we balance the atoms other than oxygen and hydrogen first. So we have 1 iron here, we have 1 iron here, and so they're balanced. Then we balance the oxygens, but there are no oxygens here. Then we balance the hydrogens, but there are no hydrogens here. Then we balance the charge. The charge on the left is +2, the charge on the right is +3. We balance out the charge by adding an electron, which is a negative charge. And so to balance this, I want to make them both +2, so I'll add 1 electron over here. And so now it's balanced. I have Fe2 plus goes to Fe3 plus an electron, or I could have just looked it up on the table. This one's on the table already, I don't have to balance it. The same thing here, if this one was not on the table, I can balance it. First, we balance all atoms other than oxygen and hydrogen. So sulfurs, I have 2 sulfurs here, 1 sulfur here. So in this case, I multiply the sulfate by 2, or change the coefficient. I can't add a sulfur here because there's no sulfur present in this reaction. And then I balance out the oxygens. I have a total of 8 oxygens over on the left. I have a 2 times 4 is 8 oxygens on the right. It's already balanced. And then I balance the hydrogen. There's no hydrogen to balance. Then I balance the charge. The charge is -2 on the left, -4 on the right. And so this is mismatched, so we need to add 2 electrons to the left. That'll give us 2 extra negative charges for the left. So I get this one, S2O8, 2 minus plus 2 electrons yields that. And so there are 2 ways I could have done this. One, if the reactions occur on this chart, I could just copy it. Or 2, if they don't occur on the chart and I know what it forms, then I can do this. This is called skeleton redox, which is back in chapter 5. Does that sound familiar? Chapter 5? Yeah. I think, as I recall, it's chapter 5. It's been a while since I did 1A. All right, so once we have the balanced chemical equation, then we can come up with the K. And in this case, are we looking for KC or KP? KC? Okay. So Kc is going to be the equilibrium concentration of the iron 3 plus squared times the sulfate squared divided by the peroxo, whatever it was called, peroxo disulfate, S2O8, times the Fe2 plus squared. That would be it there. Okay, any other questions? I did have questions about the lab from last week. We're going to have 2 types of reports for the labs that we're going to generate. One is just fill in a blank report sheet like this, fill in the blanks. The other is more formal scientific report in which we'll write it in a certain organizational structure that's typical for scientific reports. But for Le Chatelier's principle, we're just going to fill in the blanks. So they asked us for the colors. The color of copper-2 sulfate was light blue. For the tetramine copper-2 ion was dark blue or a deep blue color. After the addition, what happened? What did the color change to? So we just fill in the blanks with the colors here. Okay, then they're asking this. Explain the effects of ammonia and hydrochloric acid on the copper 2 sulfate solution in terms of Le Chatelier's principle. Consider the following equilibria. And so some students are asking, what can we put out? So the equilibrium with copper, the sulfate's a spectator, so we're looking at just copper 2 ions. These copper 2 ions, this would be from copper 2 sulfate. And the ammonia going to the tetramine copper ion, copper 2. So, okay, thank you. Okay, great. Let me just grab one of these for a morning call. So for something like this, all I want is just, you could write it out if you'd like, you know, if that's your preference, or you can just show it symbolically. So for example, if we increase the ammonia, what's Le Chatelier's principle tell you? Which direction will it shift? To the right. Okay. If we increase the HCl, what happens here? Yeah, if we increase the HCl, what's that going to do to these? If we increase the HCl, it's going to take out the ammonia. And so if we remove the ammonia, then it's going to shift to the left. Okay. So we could show that here, you know, increasing ammonia, this is going to shift it that way. Over here, if we add H+, we're going to form ammonium. And the more H+ we add, the more ammonium we form and the less ammonia we have, which is going to result in a left shift. Something like this, you know, just showing. Let's go on to B here, cobalt ions. So they're asking for the color, and then account for the changes observed for the cobalt solution in terms of Le Chatelier's principle. So we have cobalt 2, hold on. And then we add 4 chlorides to this to form the tetrachlorocobaltate 2 complex. There. So for this one, if we add HCl, so that's going to increase the chloride. So if we add HCl, that increases the chloride. Which way does it shift? Yeah, shift to the right. So just increasing the chloride. What if we add water? If we add water, what that's going to do is it's going to decrease the concentration. So if we add water to cobalt 2, it decreases the concentration. So if we decrease the concentration of cobalt 2, which way does it shift? Shifts to the left. So if we add water, we're decreasing the concentration of cobalt 2 and chloride. Shifts to the left. But the problem is everything's in the same beaker. So if I add water, what happens to this concentration? It also decreases. And so what happens is all the concentrations decrease. So I'm going to expect a shift left and a shift right. And so maybe the shifts cancel one another out. And they do. So for example, if I do that, they do cancel out, but they don't cancel out evenly unless there's the same molarity on both sides. That is this. If let's say I cut the concentration in half. If I cut the concentration in half, so this gets cut in half, this gets cut in half, and this gets cut in half, the impact is uneven. Which side is going to see a greater impact by cutting the concentration in half? The left side or the right side? The left side is going to see a greater impact. Why? Because it's more concentrated. That's why. The same thing goes, like cutting the concentration is like increasing the volume of water, increasing the volume of liquid. It's the same thing as gases. If these were all gases and I increase the volume, that is decrease the concentration, increase the volume, which side will it shift? If these were all gases, it'd shift to the side with more gas. The side with more gas would be the left side because there would be 5 moles versus 1 mole. And so 5 moles of gas requires more volume, 1 mole of gas less volume. The same thing. If I decrease the concentration, then there's more room, which accommodates this. If I increase the concentration, there's less room, which accommodates this. Now, for H2O, we can see this by K. There's going to be a different impact. So when I look at K, let's do that over here. K is going to equal the COCl4, 2 minus concentration at equilibrium, divided by the CO2 plus concentration at equilibrium, and the Cl minus concentration at equilibrium to the 4th power. If I cut the concentrations in half for everything, what I'm going to end up with is this. I'm going to have 1/2 the original concentration. So let's say I dilute it and I double the volume, half the concentration. If I had the same molarity on both sides, that is, I had just 1 and 1, then do you see the doubling will have the same impact on both sides? It would be even, and therefore there would be no shift. But because I have more moles of solution on the left side, then I have to cut this one in half as well. And this is going to be chloride, and this would be to the 4th power. There. So let's factor out this impact here. These are going to be all equilibrium. Equilibrium, this is equilibrium, this is equilibrium. And so if it were even molarity, then they would cancel. There'd be no impact, but they are uneven. So this would be 1/2 to the 4th. So that would be 1/2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So it'd be 1/16 chloride. In other words, this is going to go to this 16 times COCl4 2 minus divided by the CO2 plus and the Cl minus. This will be at equilibrium, this will be at equilibrium, this will be at equilibrium. But what we're going to see is this is no longer going to be at equilibrium because it's no longer going to equal K. And so here, this is not equal to K is not equal to this. What we call this is, we call this Q. Q is whatever ratio we have. And so K is a ratio when it's at equilibrium. So we have different scenarios. When Q is equal to K, then nothing changed. And so if all these 1/2s canceled one another out, nothing changed, Q is still K. In this case, Q is going to be greater than K. If Q is going to be greater than K, what that means is this is too big. This is 16 times too big. And so in other words, we have to make it smaller. To make that ratio smaller, it has to shift to the left. If we shift this to the left, then we're going to increase the cobalt and the chloride, decrease the tetrachloro complex, and we'll make this ratio smaller. And so if Q is greater than K, then we're going to expect to shift left. If Q turns out to be less than K, that is, let's say the 16 were on the bottom, then we have to shift it to the right to reestablish the correct ratio. And so Q is whatever ratio we have, not necessarily K. It might be, but it might not be. So we just call it Q. And the same thing here. This is not equal to K. This is equal to Q. Okay, so increasing the water means we're going to shift it to the side with greater molarity, that is, more moles of solution, and then we shift it to the bottom. Likewise, if we evaporated, this is increasing the water content and diluting it. If we evaporated the water, we're going to concentrate all of these, but the left and right sides aren't concentrated evenly, and there will be a shift. Okay, 10, they just want the observations like a milky white precipitate, 11, precipitate dissolved, forming a CCS, that kind of thing. Are there any questions about this? So this is kind of what I'm looking for. This is due Thursday. So you have some time to complete it. Uh-huh. You don't have to do the pre-lab questions. Oh, they're turning those in. Okay, let's take a look at today's lab. Let's finish the notebook prep. Like I said, the video got cut off. Some reason I thought I hit pause and didn't hit pause, and then I thought I hit record, but it didn't resume. So I ended up stopping a little early. So where did we stop at? Cool the room temperature. Okay, here, cool the room temperature. It doesn't have to be perfectly room temperature, just close. If it's still a little bit warm, that's all right. We don't want it too warm because that's going to just boil off the ethanol. We're going to waste it. And so here, we cool the room temperature. About room temperature. And then we're going to add 10 milliliters of 95% ethanol. Ethanol is abbreviated ETOH. It's okay. You want to add this slowly, not because of a violent reaction. We want to add it slowly because what we'd like to do is we'd like to get nice big crystals. Now, growing crystals is not so easy. You know, sometimes what you end up with are a whole bunch of tiny crystals, crystals that are so tiny you can't see them with your naked eye. You need a microscope to see the crystals. What we want is we want big crystals that we can actually see with our eyes. And so one of the tricks to getting big crystals is to just do the crystallization slow. If we do rapid crystallization, then typically what happens is you make a lot of little baby crystals. If you make, let's say, thousands of baby crystals, none of them can grow very big. 95% ETOH. I'm here. 10 milliliters of 95% ethanol. ETOH is common abbreviation for ethanol. So rather than nucleating thousands and thousands of tiny baby crystals, it's better to nucleate just a few crystals. If we can nucleate a few crystals, then those few crystals can grow bigger and bigger with time. And so what we want is we want to minimize nucleation, maximize growth. If you want tiny crystals, then you need to maximize nucleation and minimize growth. Sometimes we want tiny crystals because what they do is they do a process called sintering, where they take the tiny crystals and kind of melt them together. But it's not really melted together. It's just pressed together. Okay, why do we want big crystals? We want big crystals because usually big crystals mean higher purity. If we have lots and lots of tiny crystals, we can get things called co-precipitation, and we can get impurities trapped in those tiny crystals. And so, you know, when they do, let's say, things that they need really high purity for, like silicon chips, you know, the silicon chips, it's just one single crystal that they cut into wafers. There are other things where they use just one single, I mean, that's hard to do. It's hard to just nucleate one crystal and have that grow. I mean, you can do it, but it's hard. So we're going to just add this slowly. That would be a modification to that. I don't recommend stirring. Because normally when you stir, you tend to nucleate more crystals. So I would eliminate stirring from this. Okay, then we're going to further cool the beaker and its contents in ice. The cooled liquid should thicken with crystals. After cooling in ice for 15 to 20 minutes, the crystals should be collected by filtration with suction using Buchner funnel and filter flask. We're not going to filter today. We're going to try to let the crystals grow slowly overnight, basically. And we're going to collect the crystals on Thursday. So this ends day 1 of this lab. Day 2 is going to begin with the Buchner funnel. This is the Buchner funnel here. Buchner funnel can catch large amounts of precipitate. We have a piece of filter paper that's fitted for this. So this is the filter paper. You just put it on the bottom here, and then it's not adhering to the surface, so we usually just wet it down with some water so that it's stuck to the bottom of the Buchner funnel. We don't want to pour stuff in here and have it go underneath the filter and lose it into this. This is called a filter flask. It's for vacuum. It's very thick-walled, you know, and so it could withstand a vacuum. And what we do is we attach a vacuum here. The vacuum we're just going to use is the house vacuum here. Now, we don't want to suck water into the house vacuum, because if we suck water into the house vacuum, it'll destroy the vacuum pump. And so between the filter flask and the house vacuum, we need a trap. So this is the trap here. So what happens is, if this overflows, with liquid here, and the liquid will have to reach the sidearm level. It'll get sucked into the tube. It shouldn't, what people do is if it starts getting high, they stop and they dump out the liquid here or save it. Depends. Sometimes we save this, sometimes we dump it. So we could dump it to prevent it from being sucked. But in case you didn't do that and some liquid gets sucked over here, then we have this. This is going to save the pump because the liquid's going to get fed through this tube, which releases the liquid down at the bottom of this. And so this would have to fill up to the sidearm before it gets sucked into the vacuum over here. If that happens, then, kind of destroyed the pump. So this adds just a level of protection. Okay, let's take a look at the vacuum that we can generate with this. So we want to make sure there are no leaks here. Do you hear the vacuum? Okay, so you can see there's a decent vacuum here. We can also release this vacuum here. We have this little valve on the hose. So or just turn it off. Turn it off and release it here. Oops. This we should clamp because these things fall over all the time. Okay, any questions on this? Okay, so then when we do this vacuum filtration, turn it on here, make sure there are no leaks. This is a little screw clamp I have here. And then what this does is you can filter things pretty rapidly. So there's some suction here. Ends up sucking the water through here. All right. Any questions on that? So for prep, I would just, cool an ice bath. Ice water bath. Yeah. Now the amounts aren't so precise. Do you have to get exactly 10 milliliters? No. In fact, the more ethanol we add, the better, usually. But you don't want to add too much, because if you add too much, then you run the risk of precipitating other stuff out that you don't want, or crystallizing other stuff out that you don't want. And so let's look at the reactions that are happening here. So the first reaction involves this. What's this stuff called? Potassium dichromate. And what does potassium dichromate do well? What is it known for? That is, as far as chemical properties, does anything stand out, or is it pretty much unreactive chemically? Yeah, it's a powerful oxidizer. I mean, this stuff is, you gotta watch out. It's here, it's a powerful oxidizer. It's a powerful oxidizer in the presence of acid, but we do have some acid present because we're taking our potassium dichromate and mixing it with this. What's this called? Oxalic acid. The monohydrate here. We're going to mix it. There's some water around, so we're going to try to dissolve it. And so it's a powerful oxidizer. Powerful oxidizers you want to watch out, because if you have a powerful oxidizer and powerful reducer, then you're going to get an explosion. In this case, are we going to get an explosion? What stands out about oxalic acid? Well, oxalic acid is a weak acid. But as far as acids go, it's on the stronger end of the weak acid spectrum. So let's take a look at the weak acids over here. Oh, we don't even have oxalic acid on here. But oxalic acid is not one of our 7 common strong acids, therefore it's a weak acid. If we had it ranked, it's up here, near the top of the weak acids. And so what is this? Is this an acid-base reaction that we're going to have? What do you think? No, this is a redox reaction. I mean, this is a powerful oxidizer. And so it's going to try to oxidize something. Well, what is oxalic acid's redox properties? Would you say oxalic acid is electron-rich, electron-poor, or just somewhere in the middle? Well, let's take a look. What is the oxidation state on hydrogen? What's the oxidation state on oxygen? And that means carbon is +3. Okay, what's carbon's range? Carbon ranges from what to what? +4 to -4. And so this is on the electron poor end of the range. And so electron poor, that's an oxidizer, right? And so if I think about this, I'd expect this to be a mild oxidizer, but not very good because, you know, I think carbon in the +4, if you think of carbon in the +4, what comes to mind? Give me a compound that has carbon in the +4 oxidation state. CO2. Is CO2 a good oxidizer? Not really. I mean, you exhale CO2 every day. You're exhaling CO2. It's not a very good oxidizer. And so this is why I say very mild oxidizer. This is a powerful oxidizer, primarily because of what? Because of potassium? Is it a powerful oxidizer because potassium is +1? Or oxygen's -2? No, oxygen doesn't want more than -2. It's a powerful oxidizer because chromium is +6. So this is what's going to happen. Dichromate, a very powerful oxidizer, is going to react with this. Now this can lose electrons. It only has 1 electron to lose for each carbon because the carbon can go from +3 to +4. But if you think about it, this stuff should be hard to oxidize because it's already +3 and we're just taking it to +4. And so this is a very, very weak reducer. Very, very weak reducer. Well, that's good because we don't want any explosions. You know, for example, you don't want to be mixing this stuff in a beaker and have it explode into your face, right? And so we want a weak reducer. We want a weak reducer to keep the reaction under control. However, it's still a little bit violent, potentially. It's still a little bit violent, potentially, because the orange-colored mixture should spontaneously warm up almost to boiling, so it's highly exothermic. It's producing enough heat to start boiling as a vigorous evolution of gas commences. And so what's going to happen is this. What we're going to do, and I modified this procedure a little bit, we're going to use these balances over here in the back. And what these have is they have a 0 button on it. So you're going to bring a 250 milliliter beaker, place it on the balance, and then 0 it. And then what you're going to do is you're going to get some scoops of oxalic acid and scoops of potassium dichromate and then put it in there. If you undershoot it or overshoot it, don't worry about it. Don't waste any time trying to get it exact. It's a complete waste of time. Just get it close and write down what you have. The potassium dichromate from this good, and there's a balance there, and in this good. So we have 2 bottles of potassium dichromate. They're both in the hood. The reason I put potassium dichromate in the hood is because it's dangerous, for one. It's an orange powder. An orange powder, what happens is, in the past I've had it out, and then I look over there and somebody has a big dust cloud, an orange dust cloud over there, because they spilled it and then it got blown into the air, and they're inhaling potassium dichromate dust cloud. Do you want to inhale this stuff? No, I mean, it's a powerful oxidizer. It's going to oxidize all your tissue, your lung tissue and whatever else, and cause burns, severe burns, chemical burns. And so we don't. And so if you generate a dust cloud, we want to do it inside the hood so the dust gets sucked out from the lab. So, are there any other hazards for potassium dichromate? So if I wanted to learn more about potassium dichromate, where would I go to look? Well, what should I look up? Any kind of health or handling concerns? Well, actually, when you buy a bottle of this potassium dichromate, in the box comes the bottle of the chemical plus an insert. And that insert is a little sheet that tells you about potassium dichromate. Do you know what that sheet's called? The information sheet? Yeah, you can get it online, but what will you search? It has an acronym. Close. Not MDMS, but very close. Well, MSDS, Material Safety Data Sheet. That's it. But they changed the name. Do you know what the new name is? Maybe it's a little easier to remember. That's probably why they changed it. I don't know. The new name is the SDS, Safety Data Sheet. All right, so let's take a look at the safety data sheet for potassium dichromate. All right, there's a signal word here, signal word danger. And let's look at the hazard statements. May intensify fire. It's a powerful oxidizer. Toxic if swallowed, harmful in contact with skin, fatal if inhaled. Causes severe skin burns and eye damage. May cause respiratory irritation, may cause an allergic skin reaction, may cause allergy or asthma symptoms or breathing difficulties if inhaled. May cause genetic defects, may cause cancer, may damage fertility, may damage the unborn child, causes damage to organs through prolonged or repeated exposure. And so danger is the key word here. So what we want to do is, well, you probably don't even want to touch this stuff or be near this stuff, but we work with dangerous chemicals all the time. For example, gasoline. In gasoline, there are carcinogens in gasoline, there are mutagens in gasoline, things that cause genetic defects. But As long as you can handle those safely, then the risk from exposure to those is minimal because you aren't going to expose yourself to much of it. Well, the same thing here. When we handle potassium dichromate, we don't want to touch it with our fingers. We don't want to get it any on our hands. We don't want to inhale any of the vapors. So as long as we do that, then it's fairly safe. We're minimizing contact with it. And so just keep that in mind. Here it's an oxidizer, so it supports combustion. Toxic, lung damage, corrosive. A lot of people use, do you know what potassium dichromate is used for a lot? It's used in leather tanning. They got that nice tanned leather. And so the people who work with leather tanning, they use this stuff all the time, and they're chronically inhaling the fumes of this or the powder of this. And so they're the ones who really are serious health risk. But there's also chromium. This is called chromium 6. There's also chromium 6 found in concrete. These stained concrete. So our next door neighbor was doing concrete, laying a patio, and it's stained concrete. And I looked at it. I looked at the packaging. It says it contains chromium 6, and then it listed all these hazards. And this guy was generating this huge cloud of dust. This huge cloud of dust covered like 3 houses worth. It was a windy day. And so then I'm thinking all this chromium 6 is getting everywhere. Well, it was hard to avoid. Chromium 6 has a bad reputation. In fact, there was a movie made. Have you heard about this? Aaron Brockovich. There's some chromium 6 contamination in the groundwater in the San Joaquin Valley, in the town of Hinckley, and there was a cancer cluster there. People were drinking this stuff, basically. And so, Aaron Brockovich was the person who figured out what that cancer cluster was due to. Okay. Go back to this. So what I recommend doing is doing this. We'll bring 250 milliliter beakers. In one of them, we'll zero it and put the potassium dichromate. In the other 250 milliliter beaker, we'll zero it and put the oxalic acid. Then we're going to add some water to the oxalic acid. And oxalic acid is not very soluble. Most of it will not dissolve. And so we're going to just mix it up and create a suspension. It's just going to be a milky white suspension. And to that milky white suspension, we're going to tap in our potassium dichromate from the other beaker. We're going to tap it in slowly to give it a chance to react and then subside, and then add some more. It'll react and then let it subside a little bit. So we'll just add it a little bit at a time. Once we've added all of it, there's still going to be some residual potassium dichromate stuck to the walls of the beaker. Get a wash bottle and wash any residual potassium dichromate into the reaction mixture so we don't waste any of it. Okay, and then we'll just continue on from there. So watch out for the potassium dichromate. Oxalic acid is also hazardous. You don't want to eat oxalic acid. You can eat a lot of organic acids like acetic acid, but oxalic acid precipitates to make kidney stones. So you don't want that. All right, are there any questions? Uh-huh. What's that? In the second step? Yeah. So what we're going to do is we're going to have the oxalic acid, add water to that, and then in the next step we're going to add the potassium dichromate solid to it. Just tap it in. So we'll just add a little bit at a time. Does that answer your question? Was that the question? Yeah, so the potassium dichromate we're going to be adding to the oxalic acid. In the procedure, it says slowly add 3.6 grams of potassium dichromate to a suspension of 10 grams of oxalic acid and 20 milliliters of water. So we have to make the oxalic acid water mixture first and then add the potassium dichromate to that. Was that the question?
Yeah.
Yeah. It's important to have some of the water there. The water is going to quench some of the heat that's generated. You can go with more than 20 milliliters of water. You know, that's not a problem. In fact, I would recommend doing more than 20 milliliters of water. More like, 30 or 40 milliliters of water is fine. And when we do this, you're going to get some splattering happening on the inside walls of the beaker. So what we want to do is we want to rinse the splatter back in. The splatter, you're going to get black spots all over there containing this black sludge that is generated from this. Uh-huh.
So, 20 milliliters of water is going to be DI water, right?
Yes. Yeah, for any kind of synthesis. It's so noisy in here. Yeah, for any kind of synthesis, we always use DI water. Just for rough wash, we use tap water. And we don't know exactly what's in the tap water, and we don't want it to contaminate our crystals. So use DI. Okay, any other questions? All right, you're going to work individually. You're going to try to grow your own crystals for this. Okay, so individual lab. And we'll talk about growing crystals later, but I'm going to probably stop when we get to a certain point, and then I'll talk about maybe a couple of other things. But go ahead and get started for this slide. All right, if one of the half reactions occurs on the chart, then we can just copy it off the chart. Question? What's that? Yeah, no, you can just heat it to boiling and that's enough. Or you can boil it for a little longer. It's fine, but I don't think it's necessary to boil it for 10 minutes. So this reaction does occur on the chart. It's right here. It's dichromate goes to chromium 3. So rather than going through the steps of balancing this, we'll just copy it off the chart. And so this is from the chart. This is kind of from chart. And so if I copy it off the chart, what does the chart say? It says dichromate plus 14H plus 6 electrons yields 2 chromium 3 plus 7 H2O. That saves me having to balance this using the skeleton method. Does this one occur on the chart? This one does not occur on the chart. And so I have to balance it using the skeleton redox method. And so using the skeleton redox, we balance all elements other than hydrogen and oxygen. And so I have 2 carbons on the left. I have 1 carbon on the right. In this case, we balance it by changing the coefficient. And so this is going to form 2 CO2s. I can't add, carbon. Like I was saying earlier, you can't. I'd like to add carbon over here plus C, but C is either graphite or diamond. So you're not going to be sprinkling graphite or diamond into this, right? Okay, then I balance what? The oxygens or the hydrogens next? The oxygens. So I have 4 oxygens on the left. I have 4 oxygens on the right. The oxygens are balanced, so I don't have to do anything. And then I balance the hydrogens. I have 2 hydrogens on the left, and I have 0 hydrogens on the right. And so how do I balance out hydrogen? I add what? Not hydrogen gas. if I add hydrogen gas, then I have to put a tube in here and bubble hydrogen gas in there. I don't want to do that. There's this reaction. Did you put hydrogen gas in your reaction? No, so we can't. Did you put sprinkled diamonds or graphite in there? No, so we can't add that. We just have to go with what we have. What we have, though, is we have acid, and acid has H+. So I'm just going to add 2 H pluses over here, and then it's balanced. If I didn't have acid, it's okay. If I didn't have acid, I'd have to add acid to this as a third reagent. And so if there was no acid here, I'd add some HCl or something like that. That's okay because that's only what we call a pH change. pH changes are no big deal. We can do that. Versus adding diamond or adding hydrogen gas, which is more than just a pH change. Okay, after I balance the hydrogens, what do I balance? Charge. So it's neutral on the left, and then this is 0, that's +2. It's +2 on the right. And so what do I have to add? 2 electrons to which side? To the right side. And then that should be balanced. So let's check if it's balanced. When it's balanced, the atoms should balance and the charge should balance. And so 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, 4 oxygens, 4 oxygens. 0, 0, +2, -2, 0. So the charge is balanced and the atoms balanced. Okay, then what I'm going to do is I'm going to combine the 2 half reactions. When I look at the 2 half reactions, this half reaction has 6 electrons being consumed. This half reaction has 2 electrons being produced. So what I need to do is I need to multiply this one by 3. So I'm going to change this to 3. I'm going to change this to 6, 6, and then 6. So now I have 6 electrons being consumed, 6 electrons being produced. So they cancel. And then I combine the 2 half reactions. When I combine the 2 half reactions, I'm going to get this. I'm going to combine everything on the reactant side. So I have dichromate plus 14H plus 6 electrons plus 3 oxalic acids. Okay, then I combine everything on the product side, which is 2 chromiums plus 7 H2O plus 6 CO2 plus 6 H plus 6 electrons. Okay, now I'm going to simplify. I have 6 electrons on the left and 6 electrons on the right. The electrons have to cancel. What else cancels? Well, the H pluses. I have 6 H pluses here and 14 here, so I'll put 8 H pluses there. Okay, and then that looks to be it. And so let's rewrite this. So the net ionic equation will be dichromate plus 8H plus 3 oxalic acids yields 2 chromium 3 plus 7 H2O liquid plus 6 CO2 gas. Now let's make sure I didn't make an addition mistake. And so I'm just going to make sure it's still balanced. So 2 chromiums, 7 oxygens plus 12 is 19 oxygens. 7 plus 12 is 19 oxygens. 8 plus 6 is 14 hydrogens. 7 times 2 is 14 hydrogens. And then 6 carbons, 6 carbons. So all the atoms are balanced. Let's check the charge. -2 plus 8 is plus 6. 2 times 3 is plus 6. So plus 6 plus 6. The charges are balanced. And so this is the first step. The first step is to convert the chromium from chromium 6 to chromium 3, which we did. The second step is we want to form the oxalato ion. And so we're going to take the chromium 3 and then react it with the potassium oxalate. The potassium oxalate is going to supply oxalate ion. And we need 3 of these for every chromium to make the trioxalato. Chromate 3 ion. And so this will be the trioxalato. So this is the heating step here. The heating step is you want to get this to react. Do we really need to boil it for 10 minutes? I don't think so. In fact, we probably don't even need to heat this. Oxalate is an excellent ligand. It'll attack the chromium-3, regardless if you boil it or not. But the boiling will just make things react faster. And so we'll get this. And so this is step 2. Step 2 is what type of reaction? Step 1 is redox. Step 2 is, what kind of reaction is this? This is Lewis acid-base reaction. Chromium-3s are Lewis acid. Oxalate is our Lewis base. So Lewis acid base. And then you know what step 3 is? Okay, so we heat this and we get the oxalate to react with the chromium to form the trioxalato-chromate ion. And then do you know what we do? We cool it. But you know, the problem is this. Potassium salts are soluble or insoluble? Potassium salts. Group 1. Group 1 are all soluble. So that's a solubility rule in water. In alcohol, it's different. Potassium salts are a lot less soluble in alcohol. And so this is what we're going to do. We're going to take 3 potassium ions, 1 trioxalato-chromate 3 ion, and this. We're going to add ethanol to this. The more ethanol we add, the less water there is. The less water there is, the less soluble it is. Does that make sense? And so we're going to make the liquid more ethanol-like rather than water-like. And so by adding the ethanol, this is why I say, you know, it doesn't really matter. Don't waste any time getting the precise amount of ethanol. We're just going to dump in a whole bunch of ethanol. That's it. The more ethanol, the more this should precipitate. And it's going to precipitate to form this. Now, a little bit of water will get in. The water is from the solvent, and so this will form a trihydrate, solid. And so this is our precipitate. Now, when we do the precipitation, do we want to nucleate a lot of crystals or nucleate a few crystals? We want to nucleate a few crystals. So this is why I say don't stir it at this step. When we add the ethanol slowly to try to minimize nucleation and maximize growth. And then after you do that, then cool it in ice. Cooling it in ice is going to promote more precipitation, but it depends. If you already nucleated a lot of crystals, then you're going to get a whole bunch of tiny crystals. Rather, we want, so the ice bath is not really necessary. It's only if you're having difficulty getting any nucleation that you want to start with the ice bath. But go ahead and do the ice bath and then take a look. Tilt the beaker and see if you're getting any crystals on the bottom. Before you add the alcohol, make sure there's no solid in there. There shouldn't be any solid in there before you add the alcohol. Okay, and then after you add the alcohol, take a look. Okay, are there any questions on this? Yeah, you can write that in the notebook or wherever. You have to have the equations, yeah.
So, we shouldn't really be concerned with exactly how much ethanol put in.
You just need a rough idea.
Okay.
More than 20, 30, more than 30, just a rough idea.
As long as it's more than 10 that
I think you're going to need more than 10. Or do I need to write that down here? And so when we come in next week, hopefully we have some nice crystals at the bottom. but the solution here is contaminated. The solution here is contaminated with excess potassium ions, oxalate ions, and oxalic acid. As we used excess, and we made sure the chromium was the limiting reagent. So when we filter it, we have to make sure our crystals are not contaminated with the solution. Because what happens is, if this solution dries, then we're going to get white crystals of oxalic acid and white crystals of potassium oxalate on our black crystals. And we don't want that. That's called co-precipitation. And so what we need to do is we need to make sure that we wash off our crystals thoroughly. But we can't wash them with water. If we wash our crystals with water, what's going to happen? They're just going to dissolve again. And so we're going to wash them with alcohol. I think there's some 50% alcohol we're going to use as wash. Okay, so we're going to filter those with the Buchner funnel. I talked about the Buchner funnel already, right?
Yes.
Okay, and then we're going to collect our crystals and then wash them thoroughly with alcohol. And then we should have fairly pure crystals, but we can get them even purer. We can get the crystals even purer by repeating that last step. The last step is this. What we're going to do is we're going to take half those crystals and dissolve them in a minimum of water, completely dissolve them. And then we're going to add alcohol again and cool it so that we can crystallize it again. But in this case, the second crystallization step isn't going to have nearly the contaminants that the first crystallization step had. And so each time we do a recrystallization, you get it purer and purer because there are less contaminants here to wash off. Okay, that's one reason we do it. And so here, by dissolving both impurities and the compound in an appropriate solvent, either the desired compound or the impurities can be removed from the solution, leaving the other behind. Okay, so it is named for the crystals often formed when the compound precipitates out. So this is recrystallization. Another reason for recrystallization is this. The other reason is to try to grow big crystals. And so, alternatively, recrystallization can refer to the natural growth of larger, it's not ice, but larger crystals at the expense of smaller ones. So let's say you have a whole bunch of small crystals. Well, what we can do is we can try the crystallization step again. That is, dissolve those small crystals in a minimum of water, add alcohol, and then try to minimize the nucleation and maximize the growth, and try to get bigger crystals. And so it's the second attempt to get big crystals. And so we're gonna, the bigger crystals are better. Bigger crystals are pure, and therefore they're desired. People like big crystals because of that. Not everybody. Some people like small crystals because of the mechanical properties. Big crystals, it can be quite brittle. Okay, is that clear? And so this recrystallization is not part of the lab. We're going to add this in. So after we collect the crystals on the Buchner, you want to leave some space and just say recrystallization. And then we're going to attempt a recrystallization. Okay? A recrystallization is pretty simple. Dissolve it in water, add alcohol, and reprecipitate it out. Okay?
What if you don't have space?
If you don't have space, no worries, because observations take minimal space. So you just write in the observations that after this step, you try to recrystallization. It's not part of the procedure, so it's fine. You write it in the observations. Okay. Lastly, since since I divided the lab this way, and if you're done, what you could do is you could either finish the Le Chatelier's report, work on notebook prep for Thursday, or try this problem here. This problem is one I wanted you guys to do yesterday, but ran out of time. And it would be this last reaction here. The Fe3 plus 6 cyanides to make the hexacyanyl complex. This one, we would set up with the same conditions. 0.100 molar iron 3 initially, and 3.000 molar cyanide. and then solve for the equilibrium concentrations. So you could give this a shot too. Or if you don't get this today, then try this at home. See if you can do this. Same conditions as the previous problem, 0.100, 3.00 molar. Solve it for equilibrium concentration.